Good afternoon, everybody. We are from Hwa Chong Institution, Singapore. I am Si Yuan, and he is Jia Dong. Our project is titled Synthesis of a Graphene Oxide Chitosan Composite, and our project mentor is Dr. Kelvin Tan. This is Singapore. Singapore is a beautiful country with summer all around the year. The weather is very comfortable. We welcome you to visit anytime you want. This is our school, Hwa Chong Institution. This is where we have our lessons and conduct our research. So today we'll be talking about the research objective for our research, background of the materials that we have used, our methodology, analysis of our results, and our final conclusions. Let me give you a brief history of filtration. Our ancestors are able to filter large solutes like sand using simple methods like cloth. And today we have improved. We are able to filter even smaller solutes like bacteria and ions. Common filtration techniques today are nanomembranes and reverse osmosis. However, these two have their limitations. Reverse osmosis requires high pressure, which is both expensive to maintain and damaging to the film, while nanomembranes are expensive in themselves. Hence, our project objective is to create a material for water filtration that is both able to operate in low pressure and is antibacterial. This is an outline of our research. We begin with a synthesis of our composite and we'll proceed on to the filtration test.
Okay, so we will move on to the material that we are actually using in this project. And the basic material is actually graphite, which is basically made of multi-layered carbon atoms, and it does not have any functional groups attached to the carbon atoms. So upon oxidation, you can actually attach multiple functional groups to the structure. For example, carboxyl, COH, epoxies, O, and last but not least, hydroxyl, which is OH. And the material that we are using is graphene oxide, which is actually formed through layer separation of graphite. So graphene oxide is a monolayered version of graphite with the same functional groups that you observed in graphite oxide. And then the question comes, why did we actually choose graphene oxide out of all the materials out there?
So, graphene oxide has two properties that we want. One is that it is able to block solutes of hydrated radius more than 4.5 Armstrong, which is very small. Second, it has good antibacterial properties. Apart from graphene oxide, we are also using this material called chitosan. Chitosan is a polysaccharide that can be found in the shells of prawns. And this is the structure of chitosan. It again has two properties that we want. It's able to prevent bacterial growth and remove heavy metal ions.
And so we will actually move on to our reaction scheme. The first step involves initiation, free radical initiation. So as you can see, there is the formation of malic acid radicals. So what we want to do is we want to form malic acid free radicals from malic acid. And this is done through the action or through the addition of the compound manganese 3 ion, and it actually acts as an oxidizing agent, and it oxidizes the malic acid to actually give malic acid free radicals. And the same thing occurs for graphene oxide. So manganese 3 similarly acts as the oxidizing agent, and it oxidizes the graphene oxide to give free radicals. And the next step, we want to actually do the addition of the chitosan. So this is called the addition step. And what we do is we use the malic acid free radicals formed in the previous step, and it will combine with the chitosan that is in the same reaction mixture to actually give malic acid chitosan radicals. And last but not least, we want to be able to graft the chitosan onto the graphene oxide through a covalent linkage and not the physical linkage. So how it happens is through the termination step, when the two radicals, both are radicals, graphene oxide and malic acid chitosan, they will come together in a termination reaction to give you grafting of the chitosan onto the graphene oxide. And this is our overall reaction scheme. So as you can see, this is Ra is malic acid. So this entire compound is the malic acid chitosan radical, and it will actually react with the graphene oxide free radical. As you can see, it's a radical. So this dot here initially it was OH hydroxyl group. So the two hydroxyl groups have gone away to actually produce hydrogen peroxide. And of course, then actually when these two free radicals react, they actually give you the covalent linkage.
So here will be our experiment. We begin with 2 mg per milliliter of graphene oxide solution that is already pre-dispersed when we have bought it. We add malic acid, potassium permanganate, concentrated sulfuric acid, and chitosan quickly because we are having a radical reaction here and we do not want other products to be formed. We allow the reaction to be occurred in a water bath. And this is our sample. You can see that there are a lot of lumps all over the sample and the sample is broken up. This indicates that the sample has low tensile strength, which is actually not what we are supposed to see in something that contains graphene oxide. Let us take a look at the SEM pictures. This is the chitosan SEM and this is the graphene oxide. Comparing these two, we can see that in our sample, there are some major differences. Graphene oxide, though flaky, each flake is often having a smooth surface, while chitosan has a largely veiny structure. On our sample, we can see that the surface is not smooth at all. There seems to be certain veiny structures across our flakes, which is a good evidence that chitosan has grafted onto the graphene oxide.
So we will move on to the next characterization method, which is actually FTIR, Fourier Transform Infrared Spectroscopy. And as you can see, the top chart, top graph actually gives you the FTIR spectra of chitosan, and the bottom is actually our sample. And as you can see, the COC group here, there is actually a shift, and this shift actually corresponds to the interaction of the COC present in chitosan with the graphene oxide.
So moving on to the issue that we have mentioned earlier, there is aggregation across the sample, and we hypothesize that this is due to poor dispersion of our composite in water. So after reading some literature, we have found that graphene oxide, once already dispersed in water, it will be able to maintain a stable dispersion due to these hydroxyl groups and carboxyl groups. There are good sites for hydrogen bonding with water molecules. We think that the issue lies with chitosan due to the presence of the amine group, which promotes formation of physical and chemical crosslinks due to its ability to be protonated and become partially positive.
And so we actually devised a new procedure to the original one that you actually saw just now. So instead of actually leaving the reaction mixture in a water bath at 50 degrees for 3 hours, we actually put the mixture onto a hot plate and also magnetically stir it for at least 1.5 hours at 50 degrees. And the next step is we actually wanted to form a film. So to get a film, right, what we did is we used vacuum filtration, put a piece of filter paper and actually vacuum filtrated our solution or suspension onto the filter paper. And this is what we actually obtained. So as you can see, this is there is a lot of difference between this particular structure or this particular film from the previous one, and this is definitely much more uniform than the previous one. And this is of course after drying in the oven at 50 degrees for 1 day, and it also actually peeled by itself in the oven. And so looking at our project scope again, we have more or less actually completed the synthesis and characterization of the graphene oxide chitosan film, but we are looking at doing more characterization works, for example, using Raman. And of course, the most important next part of our project, which is not completed yet, is actually the filtration test. For example, carrying out our bacteria and ion filtration tests to determine the applicability of these filters in the context of a non-developed country. So that's all for us. Thank you very much. Thank you everybody for listening. We would like to extend our gratitude to the Japan Science and Technological Agency, Professor Matsuzaka and Nakazawa for inviting us here, and also of course everyone for listening. So, arigato gozaimasu.
ありがとうございます。それではせっかくの機会ですので、ご質問などございましたら挙手をお願いいたします。はい、ではマイクをお持ちいたします。
Thank you, nice talk. Thank you, nice talk. And let me ask you, you proposed the reaction mechanism. It's undergoes the radical mechanism. Is there any strong evidence? For example, if you carry on the reaction in the presence of the radical scavenger, such as galvanoxylose or something like that.
Sorry, can you repeat your question?
Okay. Have you tried the reaction in the presence of radical scavenger?
In the presence of
Radical scavenger, which eats the radical. So if in the presence of the radical scavenger, your reaction does not go well. May do not go well.
The machine you mentioned earlier, yeah, we'll take that into consideration because at this point, we have assumed that the reaction progressed as we have hypothesized because our procedure is actually based on this paper here, and the reaction scheme you have seen earlier was also proposed by them. So we have assumed that it works out just like how they did. But to actually clarify if the reaction has gone as we wanted, yeah, we'll take your point into consideration.
Okay, thank you. And one more question, okay? And you obtained the film after your reaction. Is there any information about the film? Is this a monolayer film or a double layer film or a more?
Yeah, because actually our project, right, is actually we are only actually completed with half of it. So the film that you saw just now, right, was actually one of the best that we have obtained thus far, which was why we mentioned that we still needed to actually carry out more characterization, tensile strength tests, filtration tests, bacterial tests to determine its applicability in certain countries. Because like you mentioned, it is very important to know the film, and of course also to test its flow rate, because if you don't have a good flow rate, then it's not useful as a filter membrane as well. So definitely that is actually what we are looking at testing in the near future.
Okay. I will see your result more detail later.
ありがとうございます。ではお願いいたします。
Thank you very much. So I'm sure you wish to get more information on the structure of the material you prepared. Okay. So how do you expect to get such kind of information in the future?
Yeah, so thank you for your question. So as we mentioned, right, we are looking at more characterization methods because one important issue is certain things like, for example, graphene oxide, right? It's an oxide. So you can't carry out FTIR of graphene oxide because there's going to be a lot of OH groups, so it will mask your FTIR graph. So that's why we mentioned that we are looking at doing Raman, and of course we are also looking at doing more comparison between just the graphene oxide film and our film, which is a composite between chitosan and graphene oxide. And of course, the most important part of our future research, which is actually the filtration test by using the bacteria and ion filtration to determine whether or not this filter actually has the ability to filter the bacteria and ion, which is actually part of our objective that was mentioned earlier. Yeah, but of course, research, there's a lot of things that can possibly go wrong. So we are just basically tweaking and also generating hypotheses based on the problems that we have observed and trying to actually solve them to similarly attain our desired objective. Thank you.
Thank you.
ありがとうございます。それでは、お時間も参りましたので以上とさせていただきたいと思います。イェ・チャートンさん、チェン・シュアンさんでした。どうもありがとうございました。